Let's look into differentiation with the aid of logarithms. So normally, in the case you'll recall, for an example, if let's say you have, in fact, I will even say try and recall log rules in the meantime. Log rules. Yeah, recall log rules. So, but I want to maybe we'll recall the laws maybe using, yeah, let's say functions that help us recall logarithmic rules or log rules. So for an example, if let's say we're given y equals to, let's say it's x to the power of, let's say x. So we have y equals to x to the power of x. We need to differentiate the following. So when you do inspection, the base is a function, the exponent is a function. So you cannot apply like similarly maybe to power rules and say, or exponential function, and saying maybe you want to maybe multiply the base by the derivative and say ln of the base, but the base here, it's a function, so y is in terms of x. So which means now we need to try and apply the rules of logarithms in the rules of logarithms. So if you recall that for an example, if let's say a log of n equals to 1, which wanted to say log x. So you can raise log x to the power of n and say it is equals to 1. So we'll apply similar law. We'll apply similar law. Or in a case, if let's say we use the other one of introducing log on both sides, therefore sometimes we even drop down the exponent. So we're going to try and introduce a log on both sides. But in most cases, we advise that in complex mathematics, please try and apply natural logarithm. Apply ln. So it's a log to the base e. So we'll say you apply ln y, it's equals to. Even on the other side, you apply ln and the function. Therefore, before you differentiate, you'll say ln y equals to. I hope you see that the exponent, the rule says that you can drop it down or multiply ln of x now by the exponent. So I've multiplied ln x by the exponent. Then the following part, we need to differentiate the left and the right hand side. We need to differentiate the left and right hand side. So differentiation of the right hand side. So what is the differentiation of a natural logarithm? So we know that is 1 over the function inside the log. And again, we're supposed to multiply by the derivative of the function inside the log. So what is the derivative of y? So it's dy over the x. So multiply by the derivative of what is inside the log. So on the right hand side, to say initially I said right hand side, was left hand side. I hope you see now from after applying logarithms, we have a product of functions. So now what do we have to do? We have to apply product rule. So according to product rule, we have to differentiate the f of x, which is 1, multiplied by the second function ln x. And in the second term, we need to now multiply by x and change ln x in terms of x. So derivative of ln x is 1 over x, multiplied by derivative of x, which is still 1. So in the second term, we multiply by x, derivative ln x, which is 1 over x. So therefore, from there, we know we need to make dy over dx subject of the formula. So what are we going to do? By 1 over y. You can divide by 1 over y, it's not a problem. But to avoid that, by inspect what y is doing, is dividing the numerators. So when it's dividing, it means to get rid of it, we need to multiply by y. And multiply by y on the right hand side. So we have to multiply by y on both sides. Let's see, maybe it's better. So I'll multiply by y. Even on the other side, I multiply by y. The whole the whole terms multiplied by y. So we don't multiply one term, the whole function. So both and right hand side we multiply. So that in a case, therefore y here divides y. Y will divide y. So y will divide y. Just say. So I wanted to do this, y divides y. The other side is multiplying. So y times y we have 1, y times 1 over y, we're left with dy over dx. Is equals to, on the other side, we have ln x. If I let me multiply in the factor in front, plus x divided by x, it's 1, isn't it? So that is our solution. But you need to simplify further. Simplify further. We know that y is equals to, we want to leave the right hand side in terms of x, where it's possible. So we know that y it is equals to x to the power of y is equals to x to the power of x. So substitute y is x to the power of x, and we'll have ln x plus y. Close short. Close short. So therefore that will be a solution. So what dy over dx is equals to x to the power of x in bracket ln x plus y. Okay. So I hope we can look into another rule. Differentiate the following with the aid of logarithms. But sometimes you can differentiate without applying logarithms. Some other problems you can, but using logs simplifies your problems before you change the function in terms of x. So we're going to apply ln on both sides and apply ln on the right hand side. The moment I apply ln, I drop down the exponent, which is x divided by ln x. Therefore, I have ln e. So ln e was carrying this exponent, just drop it down according to the rule that when I have, let's say the function, or maybe not function, the log of something that is having an exponent, we can drop down the exponent or multiply the coefficient of the log by the exponent. Now we can change the function in terms of x. So derivative of ln y in terms of x is 1 over y. Derivative y we're going to have, if we're changing y in terms of x, we have dy over dx. It is equals to. So please note that ln e is equals to 1. Forgot. Ln e is equals to 1. So we are looking into a function now x divided by ln x. So we are having quotient of functions here. So we're interested in x. So quotient of functions, we know the rule says that you can square the denominator, and in the numerator you multiply by the denominator. And we need to multiply by the derivative of x, which is 1. And therefore minus the numerator, we're going to derivate the denominator, which is 1 over x, multiplied by the numerator x there. Hope it's clear. So in the meantime, while we are still dividing by 1 over y or multiplying by y, when we multiply by y on both sides, we are left with dy over dx on the right hand side equals to. While we are simplifying, there we're going to have ln x. Y multiplies both sides, we'll have ln x minus 1, all divided by ln squared x, ln squared x. So here's not x which is squared, we were squaring the ln, the natural logarithm. We were squaring it. And from there, substitute back the value of y. So we said y is equals to e to the power of x over ln x. In bracket, we have ln x minus 1, all divided by ln squared x, close short. So we're done differentiating using natural and with the aid of logs to say. But even if you were using the laws of exponents, initially at the end you still have to get this. Still have to get this. Because the function always appears as it is, then the derivative of the exponent, it is quotient, we do that. So we try and prove it using exponential laws, you still get the same answer. So what has to look into one that consists of I wanted product, but let me try and take one where we're having um, where we're still having trigonometric functions. Just want to do a mixture. So let's say, for an example, we have y is equals to x to the power of tan x. So y is equals to x to the power of tan x. So we need to derivate the following. So we see that we're having a base which is a function and an exponent which is a function. So I will say it's a must to use logarithms now. So you cannot think of exponential laws. So the base is a function. It's not a constant base. So which means we try and apply logarithms. Therefore, we'll say ln, and then on the other side, we apply ln, we drop down the exponent, multiply by ln x. So apply the natural logarithm on both sides of the function. So we know the derivative of ln y, it is 1 over y. Therefore, multiply by the derivative of y, which we're changing in terms of x, which is dy over dx. Then on the right-hand side, when we have to change the function, we have a product of functions there, product of two functions. So it's tan x multiplied by ln x. Product rule comes to play. So which means we're going to derivate tan x, which is going to be x squared x multiplied by the second function, ln x. In the second term, you're going to say plus. You're going to multiply by tan x and multiply by the derivative of ln x, which is 1 over x. So it's 1 over x. Then from there, we need to multiply by y on both sides. So we'll have dy over dx, which is equals to, let me close this, dy over dx, which is equals to, multiplied on both sides. So we'll have sec squared ln x plus tan x over x. Please substitute back the value of y, which is given by x to the power of tan x. In bracket sec squared x ln x plus tan of x all divided by x. All divided by x. So that is the derivative of x to the power of tan x. X to the power of tan x. Okay, so yeah, I think we'll conclude it here. And